Welcome. In this session, for our very simple neural network, we'll do some sample computations. So let's recall what our network looks like. What it looks like is there's a couple of inputs, and then we augment that with +1, and that's going into 2 neurons. And so this neuron will receive all of those inputs, and this neuron will receive all of these inputs. So this is layer 2. And the output of layer 2 then goes to layer 3. And we take those and then we add on a +1. And then that is the output. So that's what things look like. Now, suppose that we only have 2D data, so each observation has 2 entries, and let's suppose that it looks like this. Let's suppose that our layer 3 weight, our output layer is, let's suppose it's nice and simple, it's +0.5, -0.5, and 0. And then let's suppose that our layer 2 weight matrix, so for that neuron, which is layer 2 number 1, let's suppose that that's 0.5, 0.5, 0. And then for this, let's suppose that it's 1, 1, 1. So that will define the state. Then let's suppose that the observation is a size 2 observation, and let's suppose that that's 0.5. So let's make that the layer 2 input, 0.5, 1, and now I'll augment it with 1. So the difference between the x and the layer 2 input is I'm augmenting it. And then let's suppose that y is just 1. So now we'll use the logistic activation. So now I've done all of these computations ahead of time. I encourage you to write this down and then to do these computations yourself. So what we do is we first push this forward. So the way that we do the forward computation is we take this times this, and that gives us our, so let's call that forward. What we do is we compute what's the linear response at layer 2, and that I compute as 0.75 and 2.5, and I compute the layer 2 activation, and I'll put it in a 1 form partly just for space here. I compute that as approximately 0.68, 0.92, and 1. And then I compute the derivative of that, and I'll also make that as a 1 form, and that will be 0.22, 0.07, and that'll be a 1. Oh, sorry, that's a 10. So now let's observe that these are much, much smaller than that. That's going to have some consequences later on. So now what we can do is we can now push this through. So now we know the response of this, and we pre-computed the derivative terms. So now we can compute the response of the output. So the layer 3 output, the layer 3 linear response, will be -0.12. I compute the layer 3 activation as 0.47. I compute the layer 3 derivative term as 0.25. I compute the residual error as basically 1 minus this, so that's 0.53, right? That's 1 minus that. And then we compute the objective function as being 0.14. And now we're set. So what we can also do while we're here is we can do a quick multiplication and we can get the layer 3 backpropagation values. So the layer 3 backprop is just minus the residual, so that's minus 0.53. So that sets us up so that we can now, we've gone forward. Now what we do is we go backward. So let's draw a little line here to keep things tidy. And now how do I backpropagate? And the answer is we first compute the layer 3 descent vector. So that is the backpropagation factor times this times the input transposed, and what that gives me when I do all of those computations is that the descent vector for our output layer is minus 0.09, minus 0.12, and minus 0.13. Now, of course, there are actually many more decimal places that are really, really important. This is just so that to illustrate, and this way you can, when you do your computations, you can cross-check this. So that tells us the descent. So now the layer 2 scale factor, the layer 2 scale, and now this is going to be a vector, is we take the backprop factors and multiply them by the weight vectors, and what we get is that this is minus 0. I'm going to add one decimal place, 0.66, and this will be plus 0.066. So what that's doing is we can see that the backpropagation factor started at about 1 order of magnitude, and now we've actually dropped 2 orders of magnitude through that backpropagation factor. That could be a numerical problem. So the steepest matrix for layer 2, so now I'm combining this whole layer, right? So there will be one steepest vector here, one steepest vector here, and what that will look like is this. It'll be minus 0.007, minus 0.014, and minus 0.014. And then over here, this will be 0.002, 0.005, and 0.005. So that's our steepest vector. And then when I vectorize this and rescale it, what that does is it takes this and puts it here and negates every entry. And so our layer 2 descent vector is now going to have 6 entries, so I have to leave some space, and that will be 0.007, 0.014, 0.014, and then minus 0.002, minus 0.005, and minus 0.005. And so what I've done now is I've done all of the backpropagations. Before we stop, let's make some observations here. The backprop factor for layer 3 was on the order of unity, right? It's pretty close to 1. By the time we get to the descent vector, it's an order of magnitude less, right? So this was on the order of unity. This is on the order of 1/10. The backpropagation factors for layer 2 are on the order of 1/100th, and the backpropagation descent vector is, we see a lot of things that are on the order of 1/1000th. So what's happened is that we started out with a residual error that was on the order of unity. The objective function is what it is, and then that back propagation factor starts out at an order of unity, and we end up with descent vectors that are 3 orders of magnitude smaller, 1/1000th. These all end up having numerical effects when we go to do the computations, and these effects are in part because we're using logistic activation. If we used different activation functions, we might get a different result, but this is sometimes referred to as the vanishing gradient. And here, for our simple neural network with just one input, we can see how the gradient, or the descent vector, is vanishing through our computations. What have we learned in this lecture? Well, what we did was we rewrote descent so that it can perform the computations efficiently. Instead of trying to do one gigantic differentiation, what we're doing is we're breaking it into pieces. And this is effectively a right-to-left evaluation of the chain rule when we've composed all of layers together. The forward computation finds the essential values. The gradient directions are the neuron inputs at each layer. And what we're doing is we're back propagating scale factors. These scale factors can be diminished by the derivative of a logistic function, and as we saw in one example, this effectively produces a vanishing gradient.